Welcome to today's session. In this video, we'll be exploring a fascinating problem titled Single-Threaded CPU. Together, we'll break down the problem, discuss various approaches, and analyze the solution. Let's dive in and get started. The problem involves a single-threaded CPU that can handle only one task at a time. The CPU operates under specific rules for task selection. First, if the CPU is idle and there are no tasks available, it will simply wait until a task becomes available. Second, if the CPU is idle and tasks are available, it will select the task with the shortest processing time. If there is more than one task with the same processing time, the CPU will choose the one with the smallest index. Finally, once the CPU starts a task, it will complete it without interruption, regardless of whether new tasks become available during processing. The input for this problem is a 2D array called tasks, where each task is represented as a pair, enqueue_time, processing_time. The enqueue_time specifies when the task becomes available for processing, and processing_time indicates how long the task will take. The goal is to determine the order in which the CPU processes the tasks and return this order as a list of task indices. The output of this problem is a list of integers that represents the order in which the tasks are processed by the CPU. Let's consider an example to illustrate this further. Suppose the input is 1, 2, 2, 4, 3, 2, 4, 1. Here, each sublist represents a task with its enqueue time and processing time. The output for this example is 0, 2, 3, 1, which means that the tasks are processed in the order of their indices 0, 2, 3, and finally 1. To understand this, we start at time 1 when task 0 becomes available. Since the CPU is idle, it starts processing task 0, which takes 2 units of time to complete. At time 3, tasks 1 and 2 become available. Among these, task 2 is chosen because it has the shortest processing time of 2 units. The CPU processes task 2 and completes it by time 5. At this point, task 3 becomes available, and since it has the shortest processing time of 1 unit, it is selected next. The CPU processes task 3 and completes it by time 6. Now, only task 1 remains, and the CPU processes it last. Task 1 takes 4 units of time, so it finishes at time 10. The processing order, therefore, is 0, 2, 3, 1. In another example, the input is 7, 10, 7, 12, 7, 5, 7, 4, 7, 2. Here, all tasks become available at the same time, which is time 7. The CPU selects the task with the shortest processing time first, which is task 4 with a processing time of 2. After completing task 4, the CPU processes task 3, which has the next shortest processing time of 4. Next, task 2 is selected with a processing time of 5. After that, task 0 is processed, taking 10 units of time. Finally, the CPU processes task 1 with a processing time of 12. The processing order for this example is 4, 3, 2, 0, 1. The problem also includes constraints, such as the number of tasks being up to 100,000 and enqueue or processing times being as large as 1 billion. Additionally, edge cases include scenarios where all tasks have the same enqueue time, requiring the CPU to prioritize based on processing time or index. The solution must handle large inputs efficiently to meet these constraints. To begin, let's consider the brute force approach. This method involves simulating the CPU's behavior by manually checking available tasks at every time step. For each unit of time, we examine all tasks and find those whose enqueue time is less than or equal to the current time. From this subset of tasks, we select the one with the shortest processing time, and if there's a tie, we use the task's index to break it. Once the task is chosen, we execute it and move to the next time unit, repeating the process until all tasks are completed. While this approach is straightforward and intuitive, it comes with significant computational costs. Specifically, checking all tasks at every time step takes O(n) time, and since the number of time steps can be proportional to the sum of all task processing times, the worst-case complexity becomes O(n²). This makes the brute force approach impractical for large inputs, such as when the number of tasks reaches 100,000, due to its inefficiency in repeatedly scanning the task list. To address the inefficiencies of the brute force approach, we can adopt an optimized strategy using priority queues, or min-heaps, to manage tasks dynamically. The first step in this approach is to pre-process the tasks by sorting them based on their in-queue times. This ensures that tasks are processed in the order they become available. Next, we manage task selection using a priority queue. As tasks become available, meaning their in-queue time is less than or equal to the current time, we add them to the priority queue. The queue is organized by two criteria: the shortest processing time is given priority, and if there's a tie, the task index is used as a tiebreaker. Once tasks are in the queue and the CPU is idle, we execute the task with the highest priority, again, the one with the shortest processing time. If no tasks are available, we skip ahead to the in-queue time of the next task instead of simulating time step by step. This process repeats until all tasks are executed. By combining initial sorting with a dynamic priority queue, we ensure efficient task management and minimize unnecessary operations, such as repeatedly scanning the task list. Now, let's examine the complexity of the optimized approach. Sorting the tasks initially requires O(log n) time, and managing the priority queue, adding and removing tasks, also takes O(log n) time in total, since each operation on the heap is logarithmic. Combining these steps, the overall time complexity of the optimized approach is O(log n), which is a significant improvement over the O(n² complexity of the brute force method. This makes the optimized approach well suited for the problem's constraints, where the number of tasks can reach up to 100,000. The balance between efficiency and clarity is what makes this strategy ideal. By leveraging the initial sorting step, we simplify the process of determining task availability, and the priority queue provides an efficient mechanism for selecting the next task to execute. These elements work together to ensure the algorithm performs well even for large inputs. While the optimized approach offers substantial performance improvements, it does involve a few trade-offs. One notable trade-off is the additional memory required to maintain the priority queue. However, this is a reasonable price to pay given the significant gains in computational efficiency. Another factor to consider is the slightly increased complexity of implementing a priority queue compared to the brute force method. Thankfully, modern programming libraries, such as Python's Heap, make this implementation straightforward. The key insight, or the aha moment, came from realizing that tasks could be efficiently managed by decoupling their availability from their selection. By pre-processing the tasks with sorting and dynamically managing them with a heap, we eliminate the need to repeatedly scan the task list, leading to a dramatic reduction in computational overhead. This combination of sorting and priority queue usage is what makes the approach both elegant and efficient. To solve this problem, we need to simulate how a CPU schedules tasks based on their attributes, such as when they become available and how long they take to process. Our objective is to determine the order in which these tasks are executed. The first step is to parse the input data. Typically, the input consists of a list of tasks, where each task has three attributes: the time it becomes available, the time required to complete it, and its unique identifier. We need to store this data in a structure that allows efficient operations like sorting and retrieval, which will be crucial for the algorithm's success. Now that the input data is parsed, the next step is to sort the tasks by their in-queue time, ensuring tasks are processed in the order they become available. If two tasks have the same in-queue time, we use their task IDs as a tiebreaker. Sorting up front is essential because it allows us to efficiently identify which tasks are ready for execution at any given moment. The complexity of this step is O(n*log n), where n is the number of tasks. Additionally, we use a min-heap to manage tasks that are ready for execution. The heap is ordered by processing time, and task ID serves as a secondary tiebreaker. This structure enables us to quickly retrieve the task with the shortest processing time, which helps minimize waiting times and ensures fairness. At this point, we also initialize the current time variable and set up an empty heap for task management. With the tasks sorted and the heap initialized, the next step is to simulate the CPU's behavior. We iterate through the sorted tasks while managing the heap. First, we add tasks to the heap as they become ready. A task is considered ready if its in-queue time is less than or equal to the current time. We repeat this process until no more tasks meet the condition. Next, if the heap contains tasks, the CPU executes the one with the shortest processing time, removing it from the heap. The current time is updated to reflect the execution time, and the task's ID is added to the result list. When the heap is empty but tasks remain, we fast-forward the current time to the in-queue time of the next task. This avoids unnecessary idle simulation and ensures we efficiently manage tasks. Once all tasks are processed, the result list, containing the order of execution, is returned as the output. This approach relies on several key insights. First, the combination of sorting and using a min-heap ensures both correctness and efficiency. Sorting the tasks by in-queue time guarantees that we process them in the right order, while the heap allows us to select the optimal task based on processing time. Efficient time management is another critical factor. By advancing the current time when the CPU is idle, we avoid wasting computational resources simulating empty cycles. Finally, edge cases are handled seamlessly. For example, tasks with the same in-queue time are resolved by the tiebreaker in the sorting step, and if multiple tasks are ready at once, the heap ensures the correct task is chosen first. The algorithm relies on three main data structures. First, the sorted list of tasks allows us to process each task sequentially in the correct order, which comes at a one-time cost of O (n * log n). Second, the min-heap dynamically manages tasks that are ready for execution. Inserting and removing tasks from the heap each take O log k, where k is the number of tasks in the heap. Finally, the result list stores the order of task execution, with each insertion taking O(1). These structures work together to ensure the algorithm is both efficient and easy to implement. The key operations in this algorithm include sorting, which organizes tasks by their in-queue time, and heap operations, which dynamically manage ready tasks. Together, these steps ensure efficient task selection and execution. Time management is another crucial operation, as advancing the current time during idle periods avoids unnecessary computation. When analyzing the algorithm's complexity, the time complexity is dominated by the O (n * log n) cost of sorting and the O (n * log n) cost of heap operations, resulting in a total complexity of O (n * log n). For space complexity, the heap requires O (k) memory, where k is the maximum number of tasks in the heap, and the result list requires O (n) to store the execution order. Overall, the algorithm is both time and space efficient for the given problem. To solve the single-threaded CPU problem, we start by appending the original index to each task, which helps us track the order of tasks in the final result. Each task is represented as a tuple containing its in-queue time, processing time, and original index. After that, we sort the tasks based on their in-queue time, ensuring that if two tasks have the same in-queue time, their original order is preserved. The result list will store the indices of tasks in the order they are processed, and we use a min_heap to manage tasks that are ready to be processed. The time variable keeps track of the current CPU time, and task_index points to the next task in the sorted list. Within our while loop, we check all tasks whose in-queue time is less than or equal to the current time and add them to the heap. By using a heap, we can efficiently retrieve the task with the shortest processing time. In case of a tie, the task with the smaller original index is prioritized. Once we select a task from the heap, we update the time by adding the task's processing time and append the task's original index to the result list. If the heap is empty, meaning no tasks are currently available for processing, we need to advance the time to the in-queue time of the next task in the list. This ensures the CPU does not remain idle unnecessarily. The process continues until all tasks have been processed and added to the result list. Finally, we return the result, which contains the indices of tasks in the order they were processed by the CPU. This approach ensures that tasks are executed efficiently while respecting their in-queue times and processing priorities. Here, we start by importing the necessary packages and defining our solution class. The main method, getOrder, takes a 2D array of tasks as input, where each task includes its in-queue time and processing time. To manage the tasks effectively, we first append the original indices to each task. This helps us track their positions in the input after we rearrange them. We then create an extended tasks array to store these augmented tasks. Next, we sort the tasks array based on their in-queue time. If two tasks have the same in-queue time, we break the tie by processing time, and if those are also equal, by their original indices. This ensures that tasks are ordered in a way that simplifies the scheduling process. We also initialize a result list to store the final execution order, and a priority queue, or min heap, to dynamically select the next task to process. The comparator for the heap prioritizes tasks with the smallest processing time, and in case of a tie, the task with the smallest original index is chosen. To execute the tasks, we initialize two variables, time, which keeps track of the current time, and task index, which points to the next task in our sorted extended tasks array. While the result list hasn't yet captured all tasks, we keep looping. Inside the loop, we first enqueue all tasks that are available at the current time, meaning any task whose enqueue time is less than or equal to the current time gets added to the min heap. For each enqueued task, we add its processing time and original index into the heap. Once all available tasks have been added, we check if the heap is non-empty. If it contains tasks, we process the one with the smallest processing time by removing it from the heap. We then increment the current time by the task's processing time and add its original index to the result list. However, if the heap is empty, meaning no tasks are currently available, we jump the time forward to the next enqueue time of the upcoming task in our sorted list. This ensures we don't waste any time idling unnecessarily. Finally, after all tasks have been processed and their indices added to the result list, we convert the result into an integer array. This is done using the Stream API to map each value in the list to an integer and then converting it to an array. The resulting array represents the order in which the tasks should be executed based on the problem's requirements. With this, our implementation is complete and ready to handle the scheduling of tasks efficiently. Here, we start with a basic case where the input tasks are 1, 2, 2, 4, 3, 2, 4, 1. First, we pre-process the tasks by adding their original indices, resulting in 1, 2, 0, 2, 4, 1, 3, 2, 2, 4, 1, 3. Sorting these by their enqueue time doesn't change the order since they are already sorted. Next, we initialize our variables. Time is set to 0, task_index is 0, min_heap is an empty priority queue, and result is an empty list to store the order of processed tasks. In the first iteration, at time equals 1, we enqueue the first task, 1, 2, 0, into the min_heap, making it 2, 0. We then process this task, which takes 2 units of time, so we update time to 3 and append the task's index, 0, to the result. For the second iteration at time equals 3, we enqueue the next 2 tasks, 2, 4, 1, and 3, 2, 2, into the min_heap. The heap becomes 2, 2, 4, 1, because it prioritizes shorter processing times. We process 2, 2, updating time to 5 and adding 2 to the result. At time equals 5, we enqueue the last task, 4, 1, 3, into the min_heap, which becomes 1, 3, 4, 1. We process 1, 3, next, updating time to 6 and adding 3 to the result. Finally, we process the remaining task, 4, 1, at time equals 6, updating time to 10 and appending 1 to the result. The output order of task indices is 0, 2, 3, 1. Now, let's look at an example with an idle period. The input tasks are 1, 2, 3, 4, 10, 1. After preprocessing, we add indices to get 1, 2, 0, 3, 4, 1, 10, 1, 2, and sorting by enqueue time doesn't change the order. We initialize time to 0, task_index to 0, min_heap as an empty priority queue, and result as an empty list. At time equals 1, we enqueue the first task, 1, 2, 0, into the min_heap, making it 2, 0. We process this task, updating time to 3 and adding 0 to the result. At time equals 3, we enqueue the next task, 3, 4, 1, into the min_heap, making it 4, 1. We process this task, which updates time to 7 and appends 1 to the result. Here, the CPU idles until time equals 10 because the next task doesn't arrive until then. At time equals 10, we enqueue the last task, 10, 1, 2, into the min_heap, making it 1, 2. Processing this task updates time to 11 and adds 2 to the result. The output order of task indices is 0, 1, 2. In the third example, the tasks 1, 3, 1, 9, 1, 5 all arrive at the same time. After preprocessing, we get 1, 3, 0, 1, 9, 1, 1, 5, 2. Sorting by enqueue time doesn't change the order. At time equals 1, we enqueue all 3 tasks into the min_heap, resulting in 3, 0, 9, 1, 5, 2. Processing the first task, 3, 0, updates time to 4 and adds 0 to the result. Next, we process 5, 2, which has the shortest processing time among the remaining tasks, updating time to 9 and adding 2 to the result. Finally, we process 9, 1, which updates time to 18 and appends 1 to the result. The output order of task indices is 0, 2, 1. To analyze the time complexity of our solution, we start by breaking down the operations performed. First, there's the pre-processing step, where we augment each task with its original index. This operation is linear, taking n, since we're simply iterating through all tasks. After that, we sort the tasks based on their enqueue time. Sorting an array of size n involves n*log n time complexity, making this one of the dominant contributors. Next, tasks are enqueued into a min heap. Each enqueue operation takes log k, where k is the size of the heap at the time. In the worst case, when all tasks are in the heap simultaneously, k equals n. Since each task is enqueued exactly once, the total cost across all tasks for enqueuing is n*log n. Similarly, during the processing phase, each task is dequeued from the heap exactly once. Dequeuing also involves log k operations, and across all tasks, this adds another n*log n to the total time complexity. Now, let's consider the time spent advancing the CPU's clock. If the heap is empty and the next task hasn't arrived yet, we advance the time to the next task's enqueue time in 1. This step happens at most n times, contributing only n to the overall complexity. When we combine all these operations, the dominant factors are the sorting step and the heap operations, each contributing n*log n. Therefore, the total time complexity of this algorithm is n*log n. Shifting to space complexity, the input array is augmented with the original indices of the tasks. This requires n additional space. The min heap, used to manage tasks efficiently, also requires n space in the worst case, when all tasks are in the heap. Finally, the result array, which stores the indices of the completed tasks, takes n space. These are the primary contributors to space usage in the algorithm. In terms of auxiliary space, the algorithm uses a few temporary variables and constants, which require only 1 space. Combining all factors, the dominant contributors to space complexity are the heap and the result array, both requiring n. Thus, the overall space complexity is n. To better understand the efficiency of this solution, let's compare it to a brute force approach. In a naive solution, we might scan the entire list of tasks to find the next one to process at each time step. This involves n squared operations in the worst case, as we repeatedly traverse the list of tasks. Our optimized approach, on the other hand, uses sorting and heap operations to manage task selection. Sorting tasks requires n*log n, and the heap operations also contribute n*log n, making the algorithm significantly faster with a total time complexity of n*log n. It's important to note that this optimized solution achieves big O optimality. Sorting tasks by their enqueue time is necessary to process them in order, and sorting inherently has a lower bound of n*log n. This means that the time complexity of our solution cannot be improved beyond n*log n. The use of a min heap ensures efficient task selection without introducing additional asymptotic overhead. Looking at specific scenarios, in the best case, all tasks have the same enqueue time. Here, the heap contains all tasks at once, and the algorithm's complexity is dominated by the n*log n operations for sorting and heap management. In the average case, tasks have varying enqueue times, but the total work again remains n*log n due to the same factors. Even in the worst case, where tasks arrive at widely different times and require frequent time jumps, the dominant operations still result in n*log n complexity. This consistency across cases highlights the robustness of the algorithm. To summarize, the algorithm balances efficiency and simplicity by leveraging sorting and a min-heap to manage tasks effectively. The time complexity of O(n)log n and space complexity of O(n) demonstrate significant improvements over naive approaches, which could take O(n)² time in the worst case. This combination of optimal time and space usage ensures the solution is well suited for handling the problem efficiently, even for large inputs. When solving problems like single-threaded CPU, there are a few common mistakes to watch out for. First, ignoring edge cases is a frequent issue. For example, failing to account for empty input, single-element arrays, or arrays where all elements are the same can lead to incorrect results. Imagine an algorithm that assumes at least two unique elements in the input. It might fail outright for cases like 1, 1, 1. Next, inefficient solutions are another pitfall. Using nested loops or recalculating the same results repeatedly can cause significant performance issues, especially with larger inputs. A better approach is to use optimization techniques like memoization, pre-computation, or efficient data structures. Finally, off-by-one errors are a classic mistake. These include starting from the wrong index or going out of bounds. For instance, iterating from I = 0 instead of I = 1 when comparing consecutive elements in an array can lead to incorrect results. Paying close attention to these details is critical for robust solutions. Another common challenge is misinterpreting the problem. Often, assumptions about the input, such as assuming it's always sorted or that there are no duplicates, can derail your approach. To avoid this, you should carefully read the problem statement and clarify any constraints if you're in an interview setting. Choosing the wrong data structure is another mistake that can lead to inefficiency. For example, using a list to check for the existence of an element is slower compared to using a hash set. The choice of data structure directly impacts the performance of your solution, so it's crucial to pick one that aligns with the problem's requirements and constraints. When preparing for interviews, there are some key insights to keep in mind. Recognizing problem patterns is essential. Many problems are based on recurring techniques like sliding windows, two-pointers, prefix sums, or divide and conquer. Identifying the right pattern based on the constraints can significantly simplify your approach. It's also important to explain trade-offs during interviews. For example, if you chose a heap-based solution, explain why it's more efficient than sorting in that specific scenario. Testing your solution extensively is another critical step. Walk through edge cases and small examples to ensure your solution is robust. Finally, clear communication is vital. Articulate your thought process, including how you handle edge cases, select data structures, and optimize your solution. This demonstrates not only your problem-solving skills but also your ability to collaborate effectively. To deepen your understanding, it's helpful to explore related problems. For instance, the task scheduler problem on LeetCode involves scheduling tasks with cooling periods, which requires careful prioritization. Another example is the least number of unique integers after k removals, which focuses on frequency analysis and efficient prioritization of elements. The top k frequent elements problem emphasizes identifying patterns in element frequency, while reorganized string deals with arranging characters under specific constraints. Each of these problems introduces variations of techniques like greedy algorithms, heaps, or sorting. Speaking of alternative approaches, a greedy approach is often fast and intuitive for problems that involve local optimization, though it may not work well for those requiring global optimization. Heap-based solutions are excellent for maintaining dynamic data, such as the top k elements or frequencies, but they do come with slightly higher space complexity. Evaluating the trade-offs of different approaches is a crucial part of developing efficient solutions. Sorting is another useful approach for many problems, especially when order matters. While it's simple and effective, its O(n)log n time complexity may be suboptimal for very large inputs when linear solutions are available. On the other hand, dynamic programming is a powerful technique for problems with overlapping subproblems, such as those involving optimal substructure. However, it comes with its own trade-offs, including increased space complexity and a steeper implementation curve, which can be challenging in time-constrained interviews. By understanding these trade-offs and selecting the most appropriate strategy, you'll be better equipped to handle a wide variety of problems efficiently. Thank you for joining me in solving this single-threaded CPU problem. We reviewed the problem, explored an efficient approach using a min-heap, and analyzed its complexity. Don't forget to like, subscribe, and share for more coding insights. See you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!